You guys are the small class. The other section's 29 and this one's 17. And we're in a small room. This will be the recording room, so all the lectures will be from here. Let me get rid of this picture of me. Sorry. So yeah, you know who I am. Our LA is Sean once again. Just Sean. Alex is now free from her bondage. And so now Sean's just left. So Sean will be section for both LA for both sections, and the same. He'll ask you guys in the next couple days when you want him to meet with you all, and we'll schedule that as well as my office hours. I'll explain in a second. Just like last semester, there's a homework 0, a little survey if you haven't done it yet, where I ask you about my office hours. I have more flexibility during the day this semester, so I'm gonna try to have office hours scheduled when you guys can actually show up. Unlike last semester. So I'll do my best to make those more flexible. Of course, you guys know I'm via email. That's the easiest way to get a hold of me. So I don't really have to remind you of that. So I'll talk a little bit about the class. Again, I'll talk a little bit about the course itself once we get through this stuff. Again, we're doing physical chemistry, and what you'll learn is that in last semester we did a macroscopic approach, right? We took a big box of atoms or particles, right, where we let the number of particles be round Avogadro's number, big macroscopic bulk material. We were able to calculate average quantities, right, energy, temperature, right? We use temperature to track energy in a macroscopic system. And so we derived, the laws of chemistry, kind of the way that chemistry works energetically at a macroscopic scale. And in this semester, we're not going to do that. Instead, what we're going to do is we're going to pick one molecule out of that box, or an atom or a particle or whatever it may be, and pull it out and look at it by itself. Okay, we're not going to talk about bulk properties. Instead, we're going to talk about a single molecule or a single atom. And what we'll find is that the physics and the theory and the understanding of how a molecule or an atom works by itself is very different than how the bulk works. There's going to be things that are consistent between those two scales, if you will. And there are things that are very inconsistent and very strange. All right, so we'll learn a lot of those strange things, but what we'll learn from exploring chemistry at a microscopic point of view, that we'll be able to build up a theory, build up a model that allows us to calculate anything we want in chemistry. Right? We'll be able to write down an equation even for any molecule that we can theoretically solve to learn anything we want about the molecule. It tells us everything we need to know. Properties, reactivity, energetics, spectroscopy, you name it. Right? So we're going to be tackling that this semester. It's going to be a little different. The math is a little different. The theory and the concepts are different. But the end result is exactly the same. We're looking for a model, we're looking for a theory, and understand the basics of chemistry at the most fundamental level. And that's what we're going to do today, or this semester. We'll talk more about that after I'm done with all this. Again, there's no new required text. If you haven't, I know some people didn't buy the book last semester, and that's okay. If you do want to buy a book, again, I have some suggestions here. If you haven't bought it yet, you can buy Atkins. That's at the library. You can buy it used. In fact, Atkins they often sell Atkins in 2 different small packages, like half books. There's one for the quantum and one for the thermo, and so you can buy just the quantum part too. I think it's like $30. The second book I list, if you want to buy a book, you just want a keepsake or you like to collect textbooks, Physical Chemistry by Donald McQuarrie, the Big Red Book as we call it, is an awesome book. It's the one that I learned out of, and I still write my lecture notes out of it often as a reference. So it's a really good book, but it's not required. Again, you need a calculator. You got everyone in this class has already taken last semester. We don't have any new students, so you know my expectations regarding the work. Right, so grading, things are pretty similar here as last semester. There'll be 2 exams. I polled yesterday's section about the final, and we have decided to make the final also a take-home. So there will be no in-class exams in this class. There'll be both take-homes, but the turnaround time will be shorter. Okay, so I expect that in the midterm, the turnaround time, it might be a week for the midterm like it was last year. Might be a little less than a week. But for the final, I expect like 48 to 72 hour turnaround. Okay, maybe like 3 days. I think we'll do about 3 days. So no more in-class finals. That's gone. Everything else is exactly the same. homework, 10% each, 5 homeworks probably, and a little bit of participation, which is just timely submissions, attendance. I don't record attendance, I'll just keep track in my head, and also your survey as well. That will come into the participation grade. Okay, so again, my grading policy is exactly the same as last semester. Nothing's changed, just that we now have take-homes. I don't need to tell you what I expect. You guys have already taken my class, so you know exactly what we're going to do, what I expect from you. And what I just want to talk about briefly now is the schedule. The class is going to be divvied up into 5 sections, and they build off of each other, just like last semester, but in this case, it really is. They really do build up. And the goal that we're going to have is we want to build up chemistry from the ground up, right? And so we're going to start very fundamental. Right? We're going to talk about electrons and photons, talk about very small particles, light, very simple things. Well, we'll learn that theory that we learned about understanding those things will help us apply we can use that same knowledge to think about molecules and atoms as well, more complicated systems. So we'll build that up slowly. So at the beginning, the first couple of weeks, I'll introduce you to what's called quantum mechanics. We'll learn the fundamental principles, kind of the laws, right? We learned about the laws of thermodynamics at the beginning of the semester. Here we'll learn about the laws of quantum mechanics. We'll talk about where they apply and where they don't, and how they're different. So there'll be a homework for that. It'll be kind of a lot of theory, but we'll do some problems as well and build that up. And then what we'll do is we'll apply it to toy models, right? We have to come up with some sort of box, right? Our box of gas idea that we had last semester. And luckily, quantum mechanics has lots of really useful toy models that are directly applicable to chemistry. And 2 of the ones that we're going to look at are things that are vibrating springs. We'll use that as a model for a bond. We'll take 2 masses and connect them with a spring that can stretch. And what we'll learn is that the physics of that is exactly the same as the bond. Right? We can learn everything about chemical bonding from these vibrating springs. So we'll talk about the mechanics of that and apply it to chemical systems. And then one of the most important things in chemistry, or all of physics, or the natural world, is that things, microscopic things like the spin, like they like to spin like a top. Lots of things do. Electrons do. Photons, right? Light particles, they can have angular momentum. They can spin as well. Everything has angular momentum, and so we have to talk a little bit about angular momentum. Talk about spinning tops. Molecules can also spin and rotate, and these are really, really important properties of molecules, and we can exploit them to understand things about structure and about chemistry. All right, so we'll spend some time on these simple toy models, and then we'll use them to build up an atom. All right, so we'll talk about what we call oscillators, these springs. We'll talk about spinning tops, and we'll realize that we can apply these tools directly to the hydrogen atom. And what we'll do by spring break, hopefully, we'll have a complete theory for the hydrogen atom. We'll be able to calculate anything we want for the hydrogen atom. In some ways, it will be our box of gas. It is somehow, as we'll learn, it is a solvable problem. We can write down on the board the exact equations for the hydrogen atom, the exact energies, everything about the hydrogen atom you want to know, we can calculate on the board. And so we'll build up the hydrogen atom from ground up. Okay? We'll understand how you can take a proton, electron, make an atom. And then we'll understand how you can take that idea of having 1 electron and 1 proton and expand it to larger atoms, right? Multiple protons, multiple electrons, add neutrons, right? And we'll understand that the physics of other atoms and the behaviors of bigger, more complicated atoms are very similar to hydrogen, right? We can use hydrogen as a building block. So we'll spend a good amount of time on that to understand the hydrogen atom. And then what we'll do is we'll ask the very simple question, well, what if you take 2 atoms, 2 hydrogen atoms, for instance, put them together, what happens? Right? Eventually, you're going to make a molecule, right? That's what we know anecdotally. So what we'll do is then, once we understand how an atom works, we'll put 2 and 2 together and make a molecule and understand how molecules work. All right? And we'll learn something called molecular orbital theory, which is something you typically learn in organic chemistry, but we'll learn it here. And it's a qualitative way to understand the structures of molecules and their energetics and their properties in kind of a qualitative way that allows us to make predictions about the molecules. Okay? So we'll use physical chemistry to allow us to do predictions about reactivity and about structure and about stability. All right? And the tools that we develop apply as we go down. Right? This literally just builds up. Right? We're creating small building blocks and making more complex things with them, and then more complex things with those building blocks. right? And we'll make a really simple molecule, right? We'll take two hydrogens and put them together to make H2. And what we learn from that, we realize we can apply to more complex molecules, right? Everything builds up. So it's a really nice flow. And then what we're going to find out is that we have this lovely molecule, right? We can come up on the board, we can talk about a molecule, we can think about what it looks like microscopically. But then the question is, how do we confirm that in lab, right? And what we'll learn is that the way that we probe chemistry at a microscopic level is by using what is probably the most important tool of them all. It's light, right? And spectroscopy, right? Spectroscopy is it will be our big kind of final push. So we'll spend about 3 weeks on spectroscopy. In a way that we're going to tackle spectroscopy is a little different than a normal class. Often when you teach spectroscopy, you teach as a tool. And don't get me wrong, spectroscopy is a great tool. But spectroscopy in some ways is the chemist's like most pure way. That's the most pure way we can talk to molecules and listen to them. And the amazing thing is that there's lots of different types of spectroscopies, right? Maybe you've done infrared or NMR or UV vis, all very different, you would think. But in fact, there's an underlying fundamental theory that explains spectroscopy no matter what light source you use or what you're probing. So we'll talk about that universal theory of spectroscopy, and then we'll apply it to a specific application, okay? Last semester, I tried to cram in all different applications together, and we just didn't have enough time, and you just didn't really get an appreciation for it. So what we're going to do this semester is we're going to spend a little time on the universal theory, right? Talk about what it means, what spectroscopy means from a physical point of view. And then we're going to apply it to a specific type of spectroscopy. And that's up to you which one we do. So over here on the board, I have 4 choices. I'm going to take a poll for you guys about which one we're going to focus on. Okay, and the choices are, these are kind of the classic examples of molecular spectroscopy. Of course, there are many more. But these kind of fall into the major categories of ones that we could be interested in. One is infrared spectroscopy, which we know is vibrations of molecules. We can talk about microwave spectroscopy, which is what I do, which is actually rotations of molecules. We look at molecules rotating with microwaves. We can look at UV vis spectroscopy, right, which is electronic spectroscopy, exciting electrons from the ground state to an excited state of a molecule or an atom. Or we could do something that seems completely unrelated, but in fact the theory of this helps us understand the theory of all the other ones is NMR. Okay? So we can choose any one of these and we'll study it in detail. We'll do practical NMR, we'll talk about instrumentation, we'll talk about the theory, and we'll talk about results and famous experiments and really cool things that you can do with these techniques. So, but it's up to you. So I'm going to take a poll here. Now let's see so last section wanted to do infrared. I have a feeling that's probably going to be the case here, but let's see. Who would like to do infrared? 4. How about microwave? 4, 5, 6, 7, 8. UV vis. 2, 3. NMR. No. All right. So what we'll do is we'll do a little bit of infrared and a little bit of microwave. They actually go together very nicely. We'll focus on and in fact what we'll do is we'll start with microwave, and that'll give us a very natural way to go into vibrational. So we'll do a little bit of both, but we'll focus on microwave because that's my specialty and my bias anyway. You mind making a note for me, Sean?
Yeah, I got you.
Yeah, okay, great. So the way that I kind of mentioned at the beginning of class to Sean, we're gonna focus primarily on infrared, maybe because you guys voted rotational, and I feel like I can do both of these together. Maybe I'll do the same for them as well. So maybe it'll all be, everyone gets the same content. Okay, I was kind of hoping everyone would say NMR, but that's all right. That's okay. Infrared is lovely. I'm really excited to teach microwave and infrared to you guys. So what we'll do is we'll spend a lot of time. I won't spend a lot of time on theory. We'll talk about spectroscopy theory for maybe 1 or 2 lectures. And then I'll probably spend a whole lecture talking about experiments, experimental setups. And that's one of the things I'm really passionate about. Just talk about how do we do these things, and what kind of techniques do scientists use to do really high quality spectroscopy. So we'll spend some time on the instrumentation, talk about the basic operational principles of a spectrometer, and then we'll apply these techniques. And then, again, these are really natural. In Module 2, we'll be learning about vibrating springs and spinning tops. So we can apply that theory directly here. that we've learned already. And so we'll be able to spend a little bit of time thinking about really like applications in more complex systems using spectroscopy and studying them. We'll be able to learn something, hopefully if we have time, we'll learn something what's called ultra-fast spectroscopy, which is spectroscopy that studies processes on a very, very fast time scale, on the order of 10 to the minus 15 seconds, a femtosecond. Very fast time scales. And so we can watch, in some ways, I'll show you examples of where you can watch, people use infrared lasers and lasers to watch molecules associate and disassociate in real time. Right? You can watch a molecule break apart and form back together. All right, so I'll show you some really cool results from that. There's some Nobel Prize winning work in this field. So we'll talk about that. And so it'll be more of a practical kind of discussion. And I'll also talk a little bit about using it for practice as well, right? There are some tricks to understanding how to assign a vibrational spectrum. And maybe we'll do a little bit of rotational as well in that regard. Okay, so we'll do that. So that's about the gist I have for the class. Any questions about materials, content? It's all pretty straightforward, I think. So homework 1 will get posted probably not this week, not this next week, but the week after. These due dates that are here are just tentative. I'll probably change them. As you know, I always push things back usually. So there'll be a homework for each module, and this is if you didn't see it, the midterm will cover the atom and the molecule. It actually probably will be mostly molecular science, molecular orbital theory on the midterm. So the midterm will be mostly molecular orbital theory, and the final will be spectroscopy. And it's not in class, it's take home. So that's about all I have to say about this class. Okay, real quick question. Who wants to look at the final exam from last semester? No one. Everyone's hand in the other section went up. I don't want to do it either, so let's not do it. Let's just get started. Okay. So I want to talk to you briefly today. In fact, we'll probably get out a little early today. About quantum mechanics. And why we want to study it. And why it's important to chemistry. So I want to talk about it very qualitatively. Very big picture today. And then starting on Monday, we'll probably spend one lecture doing it. One of the best parts about this class is the history. And again, the history of quantum mechanics is well known, and a lot of people, maybe you've heard about it in physics, or everyone's heard of Einstein. And this is the major event of the 20th century in physics. And the theory and the things that we're going to be learning came up originally anecdotally or empirically in the late 19th century and the early 20th century, like 1900 or so, right around the turn of the century. There were a number of really, really important experiments that were done. We'll talk about those experiments tomorrow, or on Monday, next class. But a number of experiments were done. And these experiments were some of the most sensitive, the most elegant experiments that had ever been done in the history of mankind. And what these experiments showed was that the physics and the chemistry that people understood at that time, which was, and I'm going to write it down, let me tell you what they understood in 1900. The only thing that they understood in 1900 really was that there was Newton's laws, there was Maxwell's laws for electromagnetism. So this is EM, right? They understood that light was a wave that had wave-like properties. And of course, thermodynamics had mostly been developed at that point. The things that we learned last semester, right? They understood Newton's laws, they understood electromagnetism for the most part. As we'll learn on Monday, they really didn't. And thermodynamics. And so again, they created this body of predictions, right? They said, okay, atoms and material should function in certain ways based on these laws, right? At 1900, they said, okay, this is all we need to know. It's all we need to know to really understand the universe. And so there were a number of really, really critical experiments around 1900 that realized that these laws don't explain everything. these experiments that I'll show you on Monday contradict the predictions of these three principles. All right, and that really sent physics, it actually sent the entire scientific community into turmoil because it looked like Newton and Maxwell, well, maybe not that they're wrong, or they could have been wrong, but it was clear that something wasn't well understood, right? That there was this giant gap in our understanding of the way that the world works. And so we'll illustrate about 2 or 3 of those experiments on Monday. Okay, and so let's remind ourselves what these 3 things imply. You can write one sentence for each 3 that explains it. Newton's laws just basically says F equals ma, right? F equals ma, right? That's all Newton's laws effectively say. For any system, one can track the momentum and position of a particle with respect to time. All right, so that should make sense, right? If you shoot a cannon, right? Shoot a cannonball across the Sound of Long Island. If you track that as a function of time, you know exactly where that cannonball is. You know how it's moving, and you can predict where it's going to end up. Right? That's all Newton's laws say. Right? That objects move; they have inertia. Right? They move. They have constant momentum unless they're perturbed by an outside force. That's the first law. And F equals ma. Right? And that means you can predict the position, the system. You can predict the system at any point, at any time. All right? And Maxwell's laws say light is a wave. In fact, around 1900, this seems crazy now to think about it. In 1900, they weren't even sure that they thought that light propagated from one point to another through an invisible fluid called the ether. Right? They didn't understand how light can transmit through vacuum, right? Because every other type of wave, right, like sound, has to travel through a fluid, right? It's a pressure wave through a fluid. But light can travel without a fluid, right? It can travel in the vacuum. In fact, it travels faster in the vacuum than it does in a fluid. So in 1900, they didn't even know, they thought that there was this invisible fluid called the ether. So they barely even understood light at this point. But they did understand it's a wave. And thermodynamics says that a system, right, a system at equilibrium has a temperature T. Right? You measure a temperature T. And of course, energy is conserved. And the second law, delta S has to be greater than 0. Right? We learned all these. These are just the laws of thermal. Right? So this is what they understood. Right? And this is, for at 1900, this was a complete theory. Right? They were like, we can predict anything we want. Right? We know how light works. We know how energy moves around from one place to the other. And we know how physical bodies move. Right? And what we're going to find is that in the microscopic world, every single one of these fails. Newton's laws don't apply because we'll learn that if you track a microscopic particle, if you can track its position, then you don't know its momentum, and vice versa. If you know how fast it's moving, its momentum, you don't know its position. Right? We'll learn that. And in fact, that's a key theory, a key principle of quantum mechanics, is that this idea that if you know the trajectory of your particle or your system in classical mechanics, classical chem physics or whatever, you can track it at any point. But in quantum mechanics, you can't do that. Okay. We'll also learn that Maxwell's laws fail because light's not just a wave, but it's also a particle. It's a wave and a particle simultaneously. And thermodynamics will fail because we can't assign a temperature to anything. And what we'll find is that energy is still conserved, thankfully. And entropy won't be a big deal for us because entropy is a property of a macroscopic system, right? You have to have configurations. So you have to have many particles to think about entropy effectively. But this idea of a temperature just falls apart, right? How do you define the temperature for one particle? Right? We define a temperature as an average quantity for many particles. But thermodynamics doesn't tell us anything about how things work when you just have one. Right? And so at the turn of the century, there were a number of different experiments done by famous and explanations for these experiments, by even more famous people. You've probably never heard of the people who did the experiments, but you've heard of the people who explained why they didn't work, right? Einstein, Niels Bohr, Heisenberg, Schrodinger, right? These are people who weren't experimentalists, but they're the ones that explain why these experiments didn't work. And so I'm going to talk to you on Monday about these experiments. Okay, so in 1900, they realized that these things don't work. At the microscopic scale, these things break down. The solution lies in a new theory. They had to say, okay, well, we don't know what we're doing. Our old theory doesn't explain anything, so we have to come up with a new one. And so thanks to people like, well, I just named them, Einstein, Bohr, Heisenberg. We'll talk about all the contributions of these people. They come up with this new theory called quantum mechanics. And this is the theory of small things. Quantum, the word quantum comes from the Latin for one, effectively, quantum. It's not one, but it's like a singular object, right? We're going to be talking about what we call quanta. These are basically single packets of energy, right? Don't worry about that so much, but we'll understand, be very clear why it's called quantum once we get into the material. But they realize that these old laws don't apply for these small systems. We have to come up with a new theory, which is quantum mechanics. Right? And we're going to be learning that theory. Now, we're not going to be learning it to the same depth that they learned it in 1930, 1920, but we'll learn enough that we can build up chemistry from it. And I want to talk a little bit, not really so much about what quantum mechanics really is, from a very particular point of view. We'll spend the whole semester doing that. But I want to think about it from the big picture. Because I'm sure you've heard this term before. I mean, the quantum's a big buzzword, right? Quantum computing, quantum materials, those quantum TVs and LG cells, right? This word's used all the time. What are those TVs called? Quantum dot TVs. You see this term all the time, and often the term gets misused, mainly for advertising purposes, but also other bad faith reasons. But they do all reference a specific idea, this idea of a quantum. Right? And we're going to think about quantums as the smallest indivisible part. Right? That we're going to be able to build things up from tiny little individual quanta, little tiny parts. And the physics of quantum mechanical objects just are represented by integer sums of these quanta. Right? It's a weird concept, but as of Monday, once we get through Monday, you'll understand. We'll talk about how they came up with the idea of a quantum, and what it means. The idea is it's about small things, small amounts of energy, small objects, and so on and so forth. So what I want to talk about is what quantum mechanics is and isn't, from a big picture point of view. What I want to say is, first we'll talk about the things that it is. And what we're going to find is it's a very, very powerful way to think about science, about chemistry. Because what we're going to find very quickly, well, maybe not very quickly, but eventually, is that quantum mechanics is a rigorous framework for all of chemistry. There's not a single problem in chemistry that can't be solved with quantum mechanics. You can put any molecule in front of me. It can be H2. It can be ammonia. It can be a 500 atom protein. Doesn't matter. If you've got the computing power and the know-how, you can use quantum mechanics to understand every property of that molecule. And in fact, there's even a prescription to do it exactly. We'll learn that it's impossible to do it exactly, but we can write down an equation that allows us to say, if we can solve this, either with our minds or with a computer, we can calculate everything about a given molecule exactly using quantum mechanics. It has solved every single problem in chemistry. The problem ends up being not that you can solve it. The problem ends up not being that there are problems you can't solve, but rather the framework becomes so difficult that it can be difficult to actually solve the problem you write down on the board. So every problem we write down on the board, every molecule we put, we can write something down for it, but whether we can actually calculate it or not is a different question. Right? We end up using computers for that. And we'll talk about computers and how important they are in quantum mechanics. So I want to say that this is, in some ways, this is kind of related. It's a complete theory for chemistry. I'll talk about what I mean about that, what I mean by complete. And another thing, and I'm just going to be honest with you guys, quantum mechanics is difficult. And but it's difficult for a different reason than you think. I mean, the math can be tough, but it's difficult because the concepts are foreign to a macroscopic world. There are things in quantum mechanics, in microscopic chemistry, that only exist at the microscopic level. We're going to be deriving things and thinking about things that happen in real life at the microscopic level that we can't correlate to some object that we can touch and feel. Right? In thermo, we could do that. You know, when we talked about cycles and entropy, we talked about the engine, right? We think about chemical reactions and measuring equilibrium, right? There's lots of really nice ways, or when we talk about gases and entropy, we can think about heat flowing and pressure and volume, right? These are things we can touch and feel. And think about physically, right? Think about a pot of boiling water. Right? It's really easy to do that. Maybe not easy, but you can come up with a practical example. There are things in quantum mechanics that have no analog in a macroscopic level. Things that only exist at the microscopic level. Those things can be hard to understand because you don't have a basis for understanding them. The only basis to understand them is quantum mechanics. These are things that can only be explained using this theory. And so they can be kind of weird. And it can be kind of difficult to deal with sometimes. And this is, in some ways, this is why people think quantum mechanics is hard. It's not because of the math necessarily. Math can be difficult. But because the concepts are so strange. But the microscopic world looks very, very different to what we perceive on a day-to-day basis. Okay. So now I want to talk about what it's not. The first thing I want to say is that even though it's a complete theory for chemistry, it is not a complete theory for the universe. There are things in the universe that quantum mechanics fails for completely. There's going to be, we won't talk about it, but you can get, there's a limit even smaller than microscopic. For instance, the Large Hadron Collider, the big particle accelerators that physicists use to accelerate particles to very high energies and collide them. Right? The physics of those collisions, quantum mechanics won't help us for various reasons. There are things that where quantum mechanics breaks down. They had to come up with a new theory based on quantum mechanics to explain these things. So the things that we talk about here won't be applicable to everything. There are things where it breaks down. It also breaks down at the highest limit, at large masses, right? At the scale of the universe, quantum mechanics doesn't apply at all. In fact, Newton's laws don't apply either, right? That's where relativity, Einstein relativity, general relativity applies. So it's not a complete theory, right? There is no complete theory. When we talk about a complete theory of physics or the way that we understand the universe, it's actually a conglomeration of theories, right? We use Newton's laws and Maxwell's laws for macroscopic. We use general relativity at the big scale. At the scale of chemistry, we use quantum mechanics. And at the really, really tiny scale, the subatomic scale, tiny particles, high energy scale, we use what's called quantum field theory, which is different. It's derived with assumptions from quantum mechanics, but it's a very different theory. Okay, so these are, in fact, that's something that scientists have realized in the last 100 years, is that the world kind of works in the way that we perceive it. It kind of works in little chunks, discrete chunks. There are things we understand by themselves, but we don't understand them globally. Right? We understand the universe kind of like in local regions. We have some things that work really well here, and some things that work well here, and some that work here. They don't all connect together. That connecting linkage doesn't exist yet. So it's not a complete theory. But for chemistry it is. And I'll explain eventually why quantum mechanics is perfect for chemistry. because quantum mechanics works at the scale of molecules. But we'll see that more explicitly as we go through the class. The other thing it's not is a mystical theory that explains our existence and spirituality. So one thing that we're going to learn in quantum mechanics is that there's this inherent sense of uncertainty. Well, it's hard to explain that until we see it. But every time we're going to make a measurement of something in quantum mechanics, a microscopic measurement, there's going to be some inherent uncertainty to it. We won't know it precisely. We can calculate how much uncertainty there will be. We know that precisely, but we know that the value we're going to measure is just an average. Right? And there's all these different types of really crazy things that happen due to this uncertainty in quantum mechanics. And sometimes people take those and are like, well, let's apply it to Buddhism. Right? And in fact, I had an event once. I was at a wedding, and I had a conversation with a lady who just came back from China. I told her I was a physical chemist and that I was interested in quantum mechanics, and she was like, oh yeah, I went there and learned about how quantum mechanics applies to Buddhism, and I just wanted to roll over in my grave, but obviously she didn't understand it. So it doesn't really explain anything about the world in terms of things that are intangible. It is a very tangible, concrete theory, and has very specific limitations. That's the amazing thing about quantum mechanics that I really fall in love with is that even though it's a complete theory for chemistry, right? We can describe so many intricate things in such high precision with it. But the rules that we can apply to it are very limited and rigid, much more so than it is in thermodynamics. There are certain properties that we can calculate, certain things that we can do quantum mechanically, and there are things that we can't do. And those are very clearly demarcated by the theory. So it's very limited. And what it also is not is difficult. So this is kind of a joke because it's also difficult, right? And this is part of a quantum mechanics joke because we'll learn that in quantum mechanics things can be yes and no simultaneously. Once again, that's a very difficult concept to comprehend. But if you know the thought, if you've ever heard that kind of thought question or whatever you want to call it, of Schrodinger's box, right, where you put a cat inside of it and close it, and you don't know if the cat's dead inside of it or not, right? You haven't observed what's in the box. And so in quantum mechanics, you assign that the cat is simultaneously dead and alive. And that's a very true statement. In quantum mechanics, that's what we apply. That when you don't observe something, it is simultaneously all possible options at once. So something can be yes and no simultaneously. It's our act of observation that causes it to choose either yes or no. It's a very strange concept, a very difficult one. But that's kind of the joke. It can be difficult and not difficult at the same time. And the reason why it's also not difficult in some ways is because the rules of QM are very limited and provide an explicit, what do I want to think about? Explicit logic for how to predict or quantify behavior. So remember in thermodynamics, when we wanted to understand things, we just came up with state functions, right? We said, okay, well, let's come up with Gibbs, and this is a useful way to combine energies to think about spontaneity, right? We can do anything we want with thermo, right? There's all sorts of variables. There's volume, number, pressure, temperature, right? Different types of energy. Right? And of course, Newton's laws, if you have motion, your particles in Newton's laws can move any way they want, as long as they satisfy the laws. There's lots of flexibility in here. But in quantum mechanics, there's not a lot of flexibility. There's a very, very specific prescription about how the world works at the microscopic limit, and that's the only way it works. If the rules aren't satisfied, then it's not a true physical system. Okay, so at the very least, there's a prescription that we can write down that says this is what a microscopic system, how it will behave. Okay, the difficult part is actually solving it. But at the very least, we can qualitatively sit down and really make a very, very explicit list of rules and prescriptions on how to tackle a problem. Okay? And I think that's really powerful because there's not so much creativity involved. I mean, it's not really there is creativity, but it's very rigid. And in fact, as you get more and more complex, it gets more and more rigid. In fact, the lower energy you go, this is the least rigid theory. And as you get to more and more exotic, it actually, even though it becomes more exotic, the theory gets more and more rigid. There's more and more rules that every system has to satisfy. All right, we'll talk about those rules. That'll be kind of module one. Yeah, so this is kind of what I want to say about it, is that what we're going to be able to do by the end of the semester is at the very least understand and accept the fact that we have a prescription, a way to solve any problem in chemistry we want. And I mean that. What we'll find is that the bottleneck is not that the theory fails, and then we have to come up with new theory. It's that sometimes these calculations, the calculation itself is very complicated. Because eventually you have equations on the board, you have some theory that you want to, you have something that some model for your system, and then you got to go calculate the damn thing. And it turns out that that's where the real bottleneck is. And in fact, in the 1930s, right when quantum mechanics kind of became something that you would study in school, time it became mainstream, they already understood this. Paul Dirac is a very famous quantum mechanics physicist from France. He's French, but he's English. And he has a really famous book. He wrote the first textbook on quantum mechanics in the 1930s. And in that book, he says, we have the complete theory to be able to calculate anything we want in chemistry and physics. But the calculations are intractable. We can't actually do the calculations. Right? We can write everything down, but we can't actually solve it. And it wasn't until the development of computers. It wasn't until the 1960s and 1970s, when we have actual computers to do things, that we realized that we can calculate these things. And every year since then, every decade, it's gotten better and better and better. Right? Well, I'll explain, for instance. There's a really great story, and I'll tell you guys later when we get to molecules. There was a graduate student at the University of Chicago in the 1950s. Right? His PhD thesis was to calculate the energy of the nitrogen molecule. Okay, so he had a model for the nitrogen molecule, all of its electrons. We'll talk about how you set up that model. And to solve it, right? And the end result is that you get the energy of the molecule. And think of it as it calculates the enthalpy of formation of N2. Okay? That was his task. So to calculate the enthalpy of formation for N2 from ground up, first principles. N2 is not a very complicated molecule in the grand scheme of things. So when two atoms doesn't have very many electrons, it took him 2 years to calculate, just for nitrogen. And what I'll show you is, when we get to that lecture, we'll go in, I'll bring up my computer, I'll bring my laptop, how I can do it on my phone. We'll put in nitrogen and have it calculate the same thing, and it'll be done in less than a second, right? With a free program that I downloaded off the internet. Right? That's how far we've gone in this work, where nitrogen is a PhD thesis on itself, and now I can do it in class in 30 seconds. Right? And that story is really amazing, and I'll hope to try to tell you that story as we go through it, because it's really powerful how this is one of the biggest success stories of science in the 20th centuries. Of course, there are many. Is that we went from a place in 100 years, we went from not understanding how molecules work to being able to calculate anything we want. That's really, really amazing. And it's both computers and physics and chemistry that was able to do all this together. There's a number of Nobel Prize winners that are associated with this story, as well as companies associated with Connecticut. There's a local company here whose story is integral to this history. We'll talk about that. Any questions? Okay. Geez Louise, we got quite a bit of time left. Well, because we didn't go over the exam, I'm kind of done. So yeah, let's just stop for today. Let's just stop for today because that's more or less what I got right now, and I don't really want to start these experiments, these classic experiments, and talk about these inconsistencies until we have a nice full lecture to talk about them. So let's just take a break now. Make sure to fill out that survey for me. Sean will contact you about LA hours. Yeah, enjoy the rest of your week. Thanks for coming.